Welcome to the deep dive. Okay, so you've handed us a really fascinating one this time. Bill Bryson's A Short History of Nearly Everything, plus the intro, the acknowledgments, and, well, a big slice of the science inside.
A hefty slice.
Yeah, exactly. So our mission today is basically to pull out the most, mind-blowing bits, the surprising connections about, well, everything, really.
Pretty much.
Think of it as your fast track to sounding incredibly knowledgeable without wading through the whole thing yourself.
And what really struck me right away, even before getting into the cosmic details, was just the list of people Bryson talked to.
Oh, the experts. Yeah.
Seriously impressive. You've got like Ian Tattersall from the American Museum of Natural History on human origins, John Thorstensen at Dartmouth talking astronomy, Rosalind Harding from Oxford on like the biology side. It just shows the incredible amount of sort of synthesis he did. It's not just his take, it's built on deep expertise.
Absolutely. And he kicks off with this thought that, honestly, it just floors me every time I think about it. Your existence. Just you.
Yeah.
I mean, stop and think. Trillions of atoms had to assemble just so, in this unique, never happened before, never will happen again way to make you.
And the crazy thing is, those atoms, they haven't got a clue. They're just particles doing their particle thing according to the laws of physics. They don't know they're part of you.
Right. They're mindless. Yet, for this brief window, your life, they create you, this complex, aware being.
And it is brief, isn't it? Bryson mentions the number, something like 650,000 hours for a decent lifespan.
Something like that, yeah.
And then, poof,
Yeah.
the arrangement just disassembles, the atoms wander off. Why? We don't entirely know, but the fact that it happens at all.
It is the miracle, basically. That's what he's saying.
Especially when you think how rare life seems to be out there, as far as we can tell anyway. The ingredients, carbon, hydrogen, oxygen, nitrogen, they're everywhere. Common as muck, cosmically speaking.
Right, dirt cheap.
But getting them to build something like you, that's the astonishing part. That's the magic, if you like.
Which, naturally, leads to the next big thing.
Right.
The universe itself. We just take it for granted, don't we? But Bryson really hammers home that point. There was a time when there was nothing.
Absolutely nothing. No space, no atoms, zero, zip.
So yeah, thank goodness for atoms deciding to show up.
And even then, after the universe got going, your being here now, that's another layer of improbable luck. Think about it. 99.99% of all species that have ever lived are extinct.
99.99. Wow.
Yeah. So your lineage surviving all this time, that's what he calls an extraordinary string of biological good fortune. You're basically standing on a mountain of vanished life forms.
It makes you feel a bit special, but also maybe a bit precarious.
Definitely puts it in perspective.
Yeah.
Now, this connects to Bryson's own backstory with science. He talks about this awful school textbook he had as a kid.
Oh, yeah, I remember reading that bit. It just turned him right off science.
Completely. He mentions this diagram. It supposedly showed the sun inside the Earth.
Yeah. How does that even happen?
Who knows? But instead of the big, amazing questions, it was just dry facts. He mentions anticlines and synclines, just geological folds. It missed the wonder.
The why.
Exactly. He calls it a mystifying universal conspiracy among textbook authors to make science boring, which is a real shame.
It is, because later he's on this long flight looking out the window and realizes how little he actually knows about our own planet.
Like, why are the oceans salty, but the Great Lakes aren't? Seems simple, right?
You'd think.
But, as he points out, even scientists didn't have solid answers to some of these basic questions until fairly recently.
Which is kind of reassuring in a way. It shows science is always figuring things out. It's not like some finished book of facts.
Precisely. And Bryson says he's constantly amazed by how scientists do figure things out, like, how much the Earth weighs or how old rocks are or how the universe works.
Right down to the atom.
Yeah. But then they can't reliably predict an earthquake tomorrow or even the weather perfectly next week.
That contrast is fascinating, isn't it? Knowing the immense and the tiny, but struggling with the everyday complex systems.
It really is. And a perfect example of the weird ways science works is that discovery of the cosmic background radiation, Penzias and Wilson.
Oh, the guys with the antenna hiss?
That's them. They weren't looking for the echo of the Big Bang. They were just trying to get rid of static for, I think, microwave communications.
Yeah, something practical.
Yeah.
And they found the leftover heat from the creation of the universe by accident.
And had no idea what it was at first. But they get the Nobel Prize for it.
Meanwhile, the poor folks at Princeton who were actually building an experiment specifically to find it.
Got scooped by accident. It's kind of funny, but also shows how discovery can be, well, serendipitous.
So let's go back to that very beginning, the really, really early universe. Bryson talks about Alan Guth's inflation theory.
Right. So picture this. A tiny, tiny fraction of a second after the starting gun fires, the universe just balloons out incredibly fast.
Faster than light, wasn't it? Space itself expanding.
Exactly. And in that instant, gravity pops into existence. Then boom, electromagnetism, the strong and weak nuclear forces, the fundamental rule book for everything.
Strong force holding atoms together, weak force doing radioactivity.
Electromagnetism for light and chemistry and gravity, pulling the big stuff, all born in basically no time at all.
And then just a blink later, all the particles appear. Protons, electrons.
Yeah, swarms of them. Appearing out of, well, nothing at all, as Bryson puts it. The numbers are just astronomical. 10 to the power of 79, maybe 89 of each type.
It's impossible to even visualize that number.
Completely. More particles than grains of sand on all the beaches on Earth times, well, times an unimaginable amount.
But the really mind-bending part is how finely tuned everything had to be right at the start.
Oh, absolutely critical. If gravity was just a tiny bit stronger, crunch. The whole universe collapses back on itself straight away.
And if it was a bit weaker?
Poof. Everything flies apart too fast. No stars, no galaxies, no elements forming, nothing interesting.
Even the expansion rate itself had to be perfect.
Exactly. It's this nice edge balance. Everything had to be just so for stable atoms to form, and eventually, for us to be here talking about it.
Wild. And isn't it ironic that the name Big Bang was coined by someone who hated the theory?
Yeah, Fred Hoyle. He meant it dismissively, like this ridiculous Big Bang idea, and the name just stuck. Kind of funny how history works.
Okay, so zooming in a bit. Our solar system, the stuff astronomers can do now is just incredible.
Isn't it? Bryson mentions they can detect a match being struck on the moon. Right. A single match flame.
From Earth? That's insane,
And
man.
figuring out things about planets orbiting other stars, planets we can't even properly see, or those radio telescopes.
Oh, yeah, the faint signals.
The total energy collected by all radio telescopes since they started is less than the energy of one snowflake hitting the ground.
That can't be right. Less energy than a snowflake.
That's what the calculation suggests. It shows how incredibly faint those cosmic whispers are.
Mind-boggling. Now, talking about our neighborhood, Pluto. Poor Pluto.
Ah, yes, the demotion. That definitely stirred things up.
Finding its moon, Sharon, was key, wasn't it? It showed Pluto was way smaller than they thought.
Tiny, actually. Smaller than Mercury, smaller than 7 other moons in the solar system, including our own.
So why did it take so long to find Charon? Or even Pluto itself? Were people just not looking properly?
Well, it's more about where they were looking and what the telescopes were built for. As Clark Chapman points out in the book, big telescopes usually focus on tiny, distant patches of sky for galaxies and quasars.
Right, they're not scanning a whole backyard.
Exactly. Apparently, a lot of the wider sky scanning capability was actually developed by the military for, other reasons.
Interesting. And the story of Clyde Tombaugh finding Pluto, he wasn't even a trained astronomer, was he?
Nope. Young guy, hired basically to do the tedious work of comparing photographic plates night after night, looking for tiny specks that moved.
Based on Percival Lowell's calculations?
Right. But here's the kicker. Lowell's calculations were wrong. He predicted a massive planet X based on supposed wobbles in Uranus and Neptune's orbits. Pluto is far too small to cause those wobbles.
So Tombaugh found it almost by coincidence, despite the bad math.
Pretty much. A miraculous find, as Bryson calls it. Pluto was just a tiny ice ball, nowhere near the gas giant Lowell expected.
And Lowell gets the posthumous fame partly because the name Pluto starts with his initials.
Your boat, yeah. While Tombaugh, the actual discoverer, remains relatively obscure outside of astronomy circles. A bit unfair, perhaps.
Definitely. And thinking about the solar system again, those diagrams we see, they're so misleading about the emptiness.
Oh, completely. All the stuff, sun, planets, moons, asteroids, it fills less than a trillionth of the available volume. Space is just staggeringly empty.
So maps are never, ever to scale.
Never. Can't be done on a piece of paper.
And beyond our solar system, even emptier.
Much, much emptier. Interstellar space is about the best vacuum there is. Way better than anything we can make in a lab. And the distances...
Yeah, the distances are...
sign-numbing. Proxima Centauri, the closest star, 4.3 light years away. That's, 100 million times farther than the moon.
Wow. And how long to get there by spaceship?
Current tech, at least 25,000 years, minimum.
25,000 years. Okay. So vacation plans are on hold.
Yeah, definitely. And getting to the center of our own galaxy, forget about it. Longer than human history by far.
It does give you perspective, but still, with all those stars out there, billions in our galaxy, billions of other galaxies, the odds of other life seem, well, not zero, right?
Statistically, you'd think not. The numbers are just too vast. Bryson mentions Frank Drake's equation, the famous attempt to estimate the chances of intelligent life elsewhere.
Hey, trying to put numbers on the probabilities.
It's more of a framework for thinking than a precise calculation, but yeah, it suggests we're probably not alone, even if the distances make contact incredibly unlikely.
Okay, let's bring it back a bit. There's this fascinating character, Fritz Zwicky. Brilliant, apparently, but maybe a little difficult.
That's the reputation, a bit of an eccentric genius. But he came up with some amazing ideas way ahead of their time, like neutron stars.
Neutron stars. That's when a star collapses down to incredible density.
Extreme density. Crushed down to the density of an atomic nucleus, Zwicky predicted them theoretically. A teaspoonful would weigh like 200 billion pounds on Earth.
200 billion pounds from a teaspoon.
Yep, mind-bending density. And he also figured out supernovae, those massive star explosions.
He called them the biggest bang in the universe, right? After the Big Bang itself, presumably.
Exactly. He realized these colossal explosions were linked to the collapse that could form things like neutron stars. And they're crucial, these supernovae. They forge and scatter all the heavy elements.
If stuff were made of carbon, iron.
All cooked up in stars and blasted out by supernovae. Without them, no planets like Earth, no life as we know it.
Still amazing how little we actually see up there without help. Just a few thousand stars with the naked eye.
Around 6,000 on the very clearest, darkest night. Telescopes, of course, reveal vastly more galaxies, billions of them, each with billions of stars.
So trillions and trillions of stars out there, yet seeing a supernova happen is still pretty rare.
Very rare from our vantage point. Bryson's analogy is great. Trying to spot someone lighting a birthday candle in Manhattan while you're watching from the Empire State Building. A brief flash in a vast space.
Good analogy. Okay, closer to home again. The moon. How did we get our moon?
Well, the leading theory now widely accepted is the giant impact hypothesis.
Not captured, not formed alongside Earth.
No. The idea is that very early on, maybe 4.5 billion years ago, a Mars-sized object slammed into the proto-Earth. A truly colossal collision.
Wow. And the debris formed the moon.
Exactly. Debris, mostly from the impactor and Earth's outer layers, its crust and mantle, got flung into orbit and eventually coalesced into the moon.
And that explains why the moon doesn't have a big iron core like Earth, because it's mostly made of lighter crust material.
That's a key piece of evidence supporting the theory, yeah. Lower overall density, less iron.
And Bryson points out this theory isn't actually that new, is it?
No, surprisingly. First proposed back in the 1940s. But it took a long time, gathering evidence from moon rocks, computer modeling, for it to become the consensus view. Science takes time.
It certainly does. And early Earth itself. The atmosphere sounds pretty grim.
Oh, horrible. A noxious stew, he calls it. Mostly carbon dioxide, nitrogen, methane, sulfur. No oxygen to speak of initially.
But that CO2 was important, wasn't it, for warmth?
Absolutely crucial. The early sun was maybe 25–30% dimmer than it is today. Without a strong greenhouse effect from all that CO2, Earth would likely have frozen solid.
Like a snowball Earth.
Exactly. Life might never have gotten a foothold. So paradoxically, that toxic to us atmosphere was essential for life's beginnings.
Which brings us, I guess, to some of the people who figured all this stuff out, like Isaac Newton.
Newton.
Yeah.
Can't talk about physics without Newton. Supreme genius, as Bryson puts it.
But also kind of quirky, waiting 27 years to publish calculus.
Yeah. Imagine inventing calculus and just sitting on it for nearly 3 decades. And he did the same with his work on optics, light, and color. Kept it quiet for years. Very strange guy in some ways.
But Principia Mathematica, his book on gravity, that changed everything.
Fundamentally, his law of universal gravitation, F equals G m1 over R squared, that elegant little formula.
That gives me chills.
It explained apples falling and planets orbiting with the same law. The first truly universal law of nature. Revolutionary.
And there was drama getting it published too, right? A fight with Hooke.
Oh yeah. Robert Hooke claimed Newton stole some ideas. Newton got furious and almost refused to publish the final volume of Principia. It took Edmund Halley of Halley's Comet fame to basically coax it out of him and even pay for the printing.
Halley saved the day for physics. So people started trying to measure the Earth properly for practical reasons.
Often, yeah. Like Richard Norwood trying to figure out the length of a degree of latitude more accurately. Why? Because ships kept missing Bermuda. Navigation was a life and death problem.
Makes sense. Get the Earth size right, you can make better charts.
Exactly. And then there was the whole business of measuring the distance to the sun using the transit of Venus.
Watching Venus cross the face of the sun sounds tricky.
Hugely tricky. The 1761 transit gave confusing results, but the 1769 one was key. Captain James Cook sailed all the way to Tahiti specifically to observe it.
Cook, the explorer.
That's the one. His observations, combined with others, allowed the French astronomer Joseph Laronde to make a pretty good calculation about 150 million kilometers to the sun. Remarkably close.
Amazing for the time. And then trying to weigh the Earth. How do you even do that?
Neville Maskelyne had this brilliant, slightly crazy idea. Find a big, nicely shaped mountain. Measure how much its gravity pulls a plumb line, a hanging weight slightly sideways.
Use a mountain's gravity?
Seriously?
Yep. He sent his assistant, Charles Mason, the same Mason from Mason-Dixon line fame, to find a suitable mountain in Scotland. He found Schiehallion.
Okay.
But then Mason apparently refused to do the actual surveying work on the mountain, and later just shows up in Philadelphia, ill, and dies mysteriously. Weird side story.
Very weird. Did Maskelyne manage it anyway?
He did eventually get the measurements done. It was incredibly painstaking work. And then Henry Cavendish did it more accurately in the lab later with lead balls.
Right, the Cavendish experiment.
So by the end of the 18th century, they kind of had Earth's measure,
Yeah.
its shape, size, distance from the sun, its weight.
A pretty good profile of our planet.
Yeah, but figuring out its age, that was a whole different, much tougher problem. Took way longer than splitting the atom or inventing TV, as Bryson notes. So as you can tell, you really sent us on quite a journey with this deep dive, from the absolute beginning of everything.
Right up to figuring out our own planet's basic stats.
We've hit on the sheer, unlikeliness of you being here. The universe being just right, the hidden stories behind big discoveries.
A massive scales, both cosmic and tiny.
Hopefully it gave you some of those aha moments, A few surprising facts without feeling like you're drowning in information. That's the goal, right? A shortcut to understanding.
Absolutely. Hope it sparked some curiosity, too. Maybe about what resonated most or what questions popped up.
And maybe, just as a final thought to chew on, science is always changing, always revising. What facts we hold today might look totally different in the future. And after hearing all this, what big questions about existence feel most pressing or interesting to you now? Something to ponder.